So Nyquist is a polar plot. So instead of the Bode plot where you plotted the magnitude and the phase of g of j omega versus omega in a logarithmic, semi-logarithmic manner, here you just basically plot the vector g of j omega, because you remember g of j omega is a complex number. And in the space formed by imaginary and real axes, we can treat complex numbers like what? Like a vector. They have a magnitude, they have a phase or angle, and they have a real or imaginary part. So we can do a polar plot like this, and basically the omega, the frequency, will be hidden, will be implicit. So we start at some frequency and then increase it. Let's say start at 0 and increase it to infinity, or vice versa. And then for each point omega, we find the vector g of j omega, and then it gives us one point in the complex plane. And when we connect all these points together, then we get a curve like this, and we call that a Nyquist plot. Okay, in MATLAB, the command Nyquist directly will give you the plot, or you can get the output of real and imaginary part out of it. Okay, now let's look at a few examples first, and then we go to MATLAB and look at this. So let's look at some, as I said, common transfer functions that we studied for the Bode plots, like what? Like an integrator, a derivative, first order factors or second order factors. For example, if we have a simple integrator, how does it look like in the complex plane, right? So all we need is we plug in j omega for s, and what do you think would happen? So if I do it over here for you, so our g of s is 1 over s, and then again I plug in j omega for s, so g of j omega, the complex number, is going to be 1 over j omega. And I can multiply by j and divide by j. So it is going to be j divided by j squared times omega, and we know j squared is -1. So we're going to get -1 over omega times j, right? So that is the complex number. So it has an imaginary part equal to -1 over omega, and how much real part does it have? 0, right? So how do you think that would look like? Well, of course, if I want to plot it in the complex plane, right? So if I have this to be my basically imaginary axis, and this to be my real axis, right? So this is the imaginary and this is the real. What do you think would happen when I change omega from 0 to infinity, right? And omega can go all the way to infinity. How does it look like? So if omega goes to infinity, what happens? Yes, this guy goes to 0. And when omega goes to 0, this guy goes to -infinity, right? So what do you think? Yes, and there is no real part, so it is going to be perfectly on the imaginary axis. And as omega is small, you're going to infinity. Omega gets bigger and bigger, you are converging to origin, right? So all it is a big line like this, correct? That's all it is. It is a line like this, and the direction for change of omega is in this direction. So this is where omega is going to 0, and this is where omega is going to what? Infinity at origin. So the negative imaginary axis is an integrator, right? And conversely, you can show that if, what happens? Let's say h of s is equal to s. It's a derivative. And then for s, you just plug in j omega. What happens? Well, h of j omega is simply j omega plus 0. So there is no real part. The imaginary part is j times omega. So what happens? Again, it is on the imaginary axis. Omega is small, you are at origin. Omega goes big, you are going to infinity, right? So if I call this one to be g of j omega, then I can draw another line, maybe with a different color, and this line here, I can move it, oh, sorry, like that. Okay, and this one, this is where omega goes to infinity. This is where omega is 0 for the green curve, and this is what? This is h of j omega. So the real part of the imaginary axis, the positive part of the imaginary axis is a derivative, right? And that's what you can see in the lecture. So this is a derivative on integrator. What about the first order factor? For example, if you have like a PD, correct? 1 plus s times t, or you have 1 over 1 plus s times t. How does that look like? So if it's just a PD, 1 plus st, correct? So let me maximize this. So what you have, your transfer function is, in this case, 1 plus ts. And for s, you plug in j omega, and you're going to get this guy, where this is the real part and this is the imaginary part. So you see the real part does not change. It's always 1. But the imaginary part starts at 0 and then grows all the way to infinity. So what you would get is actually this vertical line. Now, on the other hand, if 1 plus ts is in the denominator, the graph will be completely different, because now what you have is 1 over 1 plus j omega t, and the magnitude of that is, of course, 1 over square root 1 plus omega t squared, the whole thing. And angle of that is angle of numerator, which is 0, minus angle of denominator, which is tangent inverse of omega t. So basically, this is going to be your magnitude, and this is going to be your angle. And you can show that if you plot it, it is going to look like a semicircle, the way that you can see it. So the circle with omega infinity starts at 0, and as omega is going to 0 or vice versa, you are converging to 1. And this is how the system would look like. And it's not really hard to show. So first, why is it that these are the two endpoints? So if you plug in omega of 0, what happens? Magnitude is 1, clearly you can see, and angle is going to be 0, so you're going to converge here. And when omega goes to infinity, the magnitude goes to 0, and the angle is negative tangent inverse of infinity, which is negative pi over 2, right? And this vector, as you see, when omega is getting bigger and bigger, the angle of the vector, correct? The angle of the vector is getting to close to what? Negative pi over 2, because positive is measured counterclockwise. When you go clockwise, it's negative. And how can you show that it is a circle? Well, all you need to do is to find the real and imaginary part. And again, it's not hard to show. If I call this magnitude and if I call this phase phi, then x is going to be what? Magnitude times cosine of phase, and y, or instead of x, I can say real axis, because x is real axis, and y, which is the imaginary axis, is m times sine of phi, right? Again, this y is the imaginary and x is the real part. So you can show that the equation between x and y is the equation of a circle with radius of 1/2 and with the center at x of 1/2 and y of 0. And here, by the way, these are the two trigonometry formulas that I said you need to know: cosine of tangent inverse and sine of tangent inverse. So these are the two useful formulas from trigs. And here I have proven for you that in that plot, if you square x minus 0.5, which is the center, squared, plus y minus 0, which is the y of the center squared. If you do it and do the algebra, then you can show that this quantity is equal to 1/4, which is also what? 1/2 squared. So you see that that is the radius, and the center is x0 equal 0.5 and y0 equal 0. So you can easily show that for a first order system, first factor like this, the equation of this arc is, again, that is x minus 0.5 squared plus y squared is 1/2 squared. Okay. And so these are the Nyquist plots for first order factors. Similarly for second order factors, again, depending on whether everything is in the numerator or denominator. If everything is in the denominator, so you have a second order system also, then by plugging s equal j omega in the standard format where the constant is 1, if you plug in and simplify, then you can see that this is your real part, and this guy is your imaginary part. And clearly, you remember also from the past, we found the magnitude of this and the phase of that, right? You just need to go back here into one of our previous slides, and if you remember, this here, this guy was the magnitude, 1 over that, of course. So 1 over this square root was the magnitude, and then this negative tangent inverse was the phase of the system here. And here is the same thing. So now you might wonder what happens to this system when omega changes. So if you look at omega of 0, if you plug in omega of 0 here, you see that the numerator is 1 and the denominator is 1, so the real part is going to be 1, and the imaginary part is going to be 0, so you are at 0.1 and 0, which is right here. And when you let omega go to infinity, what happens? Well, if you look, the order of numerator in the real part is 2, for denominator is 4. So it should go to 0. The same for imaginary. Here is order 1, this is order 4. So when omega goes to infinity, both real and imaginary go to 0, so that's what you have here. So these 2 points are obvious in terms of magnitude. So 1 and 0, completely obvious. And if you look at the phase also, I guess I mentioned that in the past to you, that the phase at omega of 0 is 0, and the phase at omega go to infinity, if you remember, I did it in MATLAB and showed you that it actually goes to 180, and then there is a negative, so it goes to negative 180. Okay, so the first and last points are quite clear. This is what happens. And as omega changes, then you're going to get this curve. Now, this is not exactly a circular curve anymore. It looks like it, but not exactly. And here you see different curves for different values of zeta. And as zeta gets bigger and bigger, the curve span gets smaller and smaller because the damping in the system goes up. And here, the point where the imaginary value goes to 0 clearly is omega equal omega n, right? And I'm sorry, the real part, not the imaginary part. So if you look here, clearly you see if omega is equal omega n, then this whole numerator goes to 0. So you're down to only an imaginary part. So for omega equal omega n, that's the intersection point of the curve with the imaginary axis. So that's what you would see, these curves here for different values of zeta. One other thing that I wanted to mention here is the resonant. We learn about resonance, right? We learned that resonance and resonance frequency and resonance magnitude are basically what? The frequencies and the value of the magnitude at that frequency where the max happening, right? If you remember back here, let me just remind you. So if you remember here, when we have a second order system, which we are studying right now, if zeta is between, if you remember, 0 to 1 over square root 2 for this range of zeta, then the curve shows a peak, and so the frequency at which the peak occurs, we call it resonant frequency, and the value, the curve at that, we call it peak value, right, or resonant peak. So now, can we find these? So in Bode plots, they easily show themselves, right? This is the plot, of course, that's the omega, and that's the peak, but in Nyquist, can we still find the resonant frequency and the peak? And the answer is yes. What we are looking for here is the maximum magnitude of the complex number, right? So when is it that the vector of the complex number has maximum magnitude? So what is the magnitude? If we go back to this picture in general, so if any point, arbitrary point you choose on the Nyquist plot, the distance from origin, right? This distance from origin to the point of interest, this distance here is what? This is the magnitude of g of j omega. So where is it that the curve has max distance, the point on the curve has max distance from the origin? That's the resonant location, right? So what we do here, we basically draw a circle, an arc, a circular arc, centered at origin, and we make the circle bigger and bigger and bigger, right? So if you make a small circle, what happens? If you draw a small circle centered here at origin, what happens? You see, it intersects the curve at one point. If you make it even bigger, again, what happens? Again, it is going to intersect it at one point, and ultimately, when you grow it bigger and bigger to come to this radius, now what happens is that circle is only tangent to the curve, it's not cutting it. And where that is tangent, that circle is tangent to the curve, which is basically the max that you could have, so the frequency corresponding to that point is omega r, right? So omega r is the frequency of that point, which is implicit. And then this distance, this radius from origin to that point, that is mr, right? So this max distance is, max radius is mr, and I mentioned that for you over here. I added it to the lecture. So implicitly, yes, we can find it. Now, on the other hand, if your transfer function is the one with only derivatives and nothing in the denominator, right? So here, g of s is what? It's simply 1 plus 2 zeta s over omega n plus s over omega n squared, right? So nothing in the denominator. So in this case, if you plug in for s equal j omega and find the magnitude and the phase, or the real and imaginary part, this is your real part, this is your imaginary part. And again, here you can show that when omega is 0, again, you are at 0.1 and 0. Just like here, and then as omega goes to infinity, the magnitude is not gonna go to 0 like this case. The magnitude is gonna go to infinity and the angle goes to positive 180. So it is gonna be this curve like this. Okay, so it's kind of like a, I would call it an exponential or a logarithmic curve, while this one is more kind of like an arc or circular. They're not exactly any of those, but that's how they look like. So these are second order systems, Nyquist. This is a first order factors, first order system, PD. and then derivative and integrator, right? And of course, constant is very easy, right? If you have a constant, what does it mean? A constant is only a real part, right? And no phase. So when omega changes, the point does not move. So your whole Nyquist plot will be a single point at the location, somewhere under a real axis. And these are, again, this is a summary of what you have for different systems, right? So this is an integrator, right? This is 1 over s. Transfer function, this is clearly, all you need is replace j omega with s. This is 1 plus ts over ts. This is 1 plus ts. This is s. Right, a derivative, this is double integrator. This is the high pass filter ts over 1 plus ts. Correct, so if you remember, this was a high pass filter, right? If there was a 1, it was a low pass filter. This is a high pass filter. And then we have other systems too, like this one, which is 1 plus ts divided by 1 plus ATS, where A is bigger than 1. So it looks like a compensator, if you remember. This has 3 and so on and so forth. So these are different other types of systems that you might see the Nyquist plot. And as I said, all you need is in MATLAB, you run the command Nyquist, okay, which I mentioned here for you. The only important thing is this. When you run the Nyquist command in MATLAB, it plots it for both positive and negative omega if you do not pass the range for a frequency, okay? It will do it for both positive and negative, and you have to be careful about that. So let me show you. For example, I'm going to do the Nyquist plot for this system 1 over 1 plus ts, right? You see it's just a semicircle below the real axis, right? But now, if I do it in MATLAB, so this is what we do. We come here and we say, let's see. So the system is 1 over 1 plus ts. So we have to change it a little bit, right? Because it's 1 plus ts. So it should look like this, right? T is 0.5, and that is your system, 1 over 1 plus ts. Again, T of 0.5, and now we say Nyquist of the system, right? And if you look here, I expected a semicircle below the real axis, but I see a full circle now. And all you need is use the data tip or data cursor. If you click here, you see positive frequencies. Okay, so you see here the frequency is 9, right? And as you move the point using cursor, you see as I'm getting closer and closer to the origin, the frequency goes toward infinity, right? You see it's raising higher, 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 it gets bigger and bigger. And now here it doesn't really show infinity, it shows like 1,000. But and as I go toward 0.1 and 0, the frequency moves toward what? Moves toward 0, right? So you can see that. Correct? Now, if I move it to the part of the curve above, look at the frequencies now. So I move it here. Look, the frequency is -3. So we are not in this section of the chapter dealing with negative frequencies, and as I mentioned in the passing class, negative frequency is not something that we deal with in mechanical or aerospace engineering, because we define frequency to be reciprocal of a period, and we use a positive period value. So why is it that MATLAB is doing such thing and showing the Nyquist for negative frequencies? We'll look at it later. That's for the Nyquist stability theorem, which uses a range of frequencies from negative infinity to positive infinity. And then we look at the Nyquist plot, whether it loops around the point -1 and 0. So at the moment, if you want to plot the Nyquist, just be aware that MATLAB does both positive and negative frequencies, but if you want to report anything, you just consider the portion of it with positive frequency. So just keep that in mind. Now, let's do one example of a Nyquist plot and solve it first by basically doing it on the paper. We can do it in MATLAB too if we want to, but I would rather first just show you with hand instead of with MATLAB. So what I want to do is, at this point, I want to plot the Nyquist of this function here, this transfer function. So here g of s is e to the negative L times s divided by 1 plus ts. So that's basically the same as this first order system. I can say multiplied by 1. So that's this first order system, which has a what, if you remember. Exponential s means delay. So it has L seconds of delay, right? So it is a first order system that has a delay of L seconds. How does that look like? Because we learned that if that e to the negative ls was not there, how would it look like? Yes, it was the semicircle, right? It was this guy here. But now that we have a delay, does it make any difference in the Nyquist plot? What was the effect of delay, if you remember, in the Bode plot? Yes, it was continuous increase in the phase as omega goes to 0. If you remember, this was this guy here, right? This is slide. Transport lag and Bode plot. So instead of the phase of the system approaching a constant number as omega goes to 0, it keeps increasing, or we can say decreasing if we are considering the negative part. So the frequency, the phase of the system was constantly, in terms of magnitude, increasing or overall decreasing, right? That was the effect, continuous change of phase. But what about the Nyquist plot? What's the effect on the Nyquist plot? And well, let's do that here manually. So if I go to Microsoft OneNote, and here we'll try to define it as g of s is e to the negative L times s divided by 1 plus ts, and for s we plug in j times omega. So g of j omega is e to the negative L j omega divided by 1 plus tj omega. And now what is the magnitude, what is the phase of this? So what is the magnitude? It's the magnitude of numerator divided by denominator. Now what is the magnitude of numerator? If you remember anything from complex numbers, you know that based on the Euler's formula, e to the negative Lj omega was what? Was cosine of L omega minus j times sine of L omega. And magnitude of this complex number is, of course, what? Real part squared plus imaginary part squared, which is 1. So the magnitude of numerator is 1. The magnitude of denominator is, of course, 1 plus omega squared t squared, the whole thing under square root. So basically, this magnitude is exactly the same as the first order system without delay. If I only had a 1 here in numerator, that had the same magnitude. So the delay is not going to affect the magnitude, but what about the phase? What happens to the phase of g of j omega? Is that going to change anything? So it's the phase of numerator minus denominator. What is the phase of numerator, which is this complex number? It's arctangent of what? Imaginary over real, right? So it's negative sine omega L divided by cosine omega L, and then minus, and you know that the angle of 1 plus tj, it was t times omega divided by 1. So if I simplify it, it is what? So you know this is tangent, right? Sine over tangent, and tangent inverse and tangent would cancel out. The negative comes out, so it is going to be negative omega L minus tangent inverse of omega t. So magnitude is the same. What about phase? This part of the phase is the same, but now I have an additional part. And this additional part keeps decreasing as omega gets bigger and bigger. So now if I compare it against the first order system, if you remember, the first order system was when omega was 0, you were at 0.1 and 0. When omega went to infinity, you were at 0.00, right? Now what about here? If I look at this case, when the magnitude is the same, no difference. What about the phase? What's the only difference in phase? So in the previous case, the phase, let me again go take a look with you. So when omega was 0, phase was 0. When omega went to infinity, phase was going to negative pi over 2. So all the phase could change was literally between 0 to negative 90 degrees. And that's what you see from 0, right? Let me show you again here. So all you can see is the phase of the initial vector is 0, and the phase of the final vector is negative 90 degrees. But in the case of this new system, the phase keeps changing. So although the magnitude will ultimately shrink to 0, but I will cross this real axis several times, right? Because again, look at the phase. When omega goes to infinity, what happens? This term, right? So when omega goes to infinity, what happens to g of j omega? This term, yes, this term goes to negative 90 degrees, but what about this? This term goes to negative infinity, the first term minus 90 degrees. So it goes to negative infinity. So the angle just keeps increasing, although the magnitude is shrinking. And so when you combine them, you see this spiral, right? So if I want to really plot it, again, here is when omega is 0. And as omega goes to infinity, you go through this spiral and ultimately shrink to 0. So it creates this twist from the simple semicircle that you had here to this spiral over there. Now, one of the things that I deliberately added here was for you using MATLAB to analyze this system. And you might say, well, this is not a simple linear system, right? If you remember, g of s in this case is what? Is 1 over 1 plus ts. So this is a linear system, but times e to the negative l times s. What do we do about this part? This is not really linear. It's a delay. It's a nonlinear behavior. So can we use the command transfer function and then Nyquist to plot a linear system with delay? Is such a thing possible? Because when you use the command transfer function, if you remember, transfer function takes what? Num and denom. It takes an array for numerator, which is in this case 1, and for denominator, which is t and 1. What about this extra delay? Is there any way, any command in MATLAB that I can also specify an extra addition for delay? And the answer is yes. We haven't used it so far, but now it's a good time to use it. So this is the command in MATLAB. So what you can say is, I'm gonna replot for you the 1 plus ts over 1 over ts plus 1, where t is 0.5, But now I have this extra basically input argument, right, which says and input delay of so many seconds, and I say 3 here. I assume L is 3. You can use any number that you want, right? So don't forget that I have an option in MATLAB where you can specify input delay. So you have to say, yes, I want so many seconds of input delay, and here I use L seconds for input delay. And this command will create a linear system with delay, and then yes, I can run the Nyquist, Bode, or any other command on it. So let's do it. So here again I use T of 0.5 and L of 3, and there we go. Look, now I have that exponential there, and now I can run the command Nyquist. And here you might say, where is that the spiral gone? Well, it's still here. Just remember that, what's the difference here? You have 2 spirals on the top of each other. This is the bottom spiral. This is what we have here. And the top one is for negative frequency. So this is 2 spiral mixed together. Okay, now that you have seen we can do systems, linear systems with delay, let's move on. And by the way, I have added this command as typed instead of just in written to the slides for you. One last note about Nyquist is the effect of system order and type on the Nyquist plot. And so one thing, order is, we know it's the highest power of S in the denominator. What you can see here on the right plot is the difference between order of denominator and numerator, n minus m. And here we assume that n is bigger than m, the system is causal. And so if n minus m is equal to 1, 2, or 3, regardless, as omega goes to infinity, the system always converges to the origin. And that is clear from the definition, right? If you look at the definition of the transfer function on the right side, this one, when n is bigger than m, as omega goes to infinity, the power of omega is bigger in the denominator than numerator. So if you look at the magnitude, magnitude always goes to 0. Now, what's the difference if n is 1 or 2 or 3 or 4 times 4 units bigger than m? What's the difference? The only difference is the direction at which these curves, the Nyquist plot curve, approaches origin. So they will all approach origin, but from which quadrant, basically, that depends on n minus m. So let's say n is bigger than m by 1, so n is 1 plus m. What happens? The only thing that it would affect is the phase of this, because phase of g of j omega is phase of numerator minus denominator. And when n is bigger than m by 1, what happens? So if you remember, for a first order system that we just looked, it was 1 over 1 plus ts, right? So what happened in the system? It was, if you just go back, it was this guy here. So you see here n is bigger than m by 1, and you're approaching 0 by angle of negative 90 degrees, right? And a similar thing happens here. You see they're both approaching the system with angle negative 90 degrees, but from, they might first, the angle might go more than, less than negative 90, so it goes to negative, for example, here. If you look, if I draw, let's say this is a point here on this curve, if I connect it to origin, the angle is now like negative 120 and then converges to negative 90, or no, actually it is like negative 70, negative 80, and negative 90 ultimately. So whether the angle can surpass -90, pass it and go to smaller numbers, or no, it is always bigger than that, it gives us these two types of curves. And this can happen when n is bigger than m by 1 units. Okay, so for example, if this is a system like this, or it could be something like this, for example, 1 plus t1s divided by 1 plus t2s plus t3s squared, right? This is the same thing. N is bigger than m by 1, but we increased both orders by 1. So m is 1, n is 2, still n minus m is 1. And if you plot the Nyquist of this, it might look like the one here instead of this one. Well, if n minus m is 2, the ultimate phase is going to be -180. Again, whether you always bigger than 180, or you can go to like -200 and then come back. That is for n minus m equal 2, and then 3, the phase is going to be -270. Okay, so this means that the phase is approaching -180 as omega goes to infinity. Here, the phase is approaching -90 as omega goes to infinity, and here, as omega goes to infinity, the phase is approaching -270. So that's the effect of order, or the difference in order of numerator and denominator on the Nyquist plot. Now, what about the type of the system? Type, if you remember, type was the number of poles at 0. Type was this parameter lambda. And what's the effect of that? Well, the effect of that is on the other side when omega approaches 0. We know when we have a 0 in the denominator and omega approaches 0, what happens? You're dividing a number by 0, and so the magnitude will increase indefinitely, goes to infinite, right? So if you look here on this graph on the left, this is the effect of type. And although you see all of them as omega goes to infinity, all of them are approaching, regardless of type or order, they're all approaching 0. But look at the other side of the curve. So this is a system type 0, where there is no s in the denominator. What happens? When the system omega goes to infinity, omega is 0, you're looking at what? Just plug in a 0 here and assume that lambda is also 0, so there is no s. Then you're going to be down to k, right? So this value here is going to be k. And then that is where omega is 0. But if system is type 1, so lambda is 1, then you're dividing the number by 0 when omega goes to 0. So the magnitude goes to what? If you see this curve, look, it starts from here at infinite and then converges to 0 as omega goes to infinity. Similarly here and similarly here, right? So if you look for a system type 1, 2, or anything bigger, when omega is 0, the magnitude is going to what? To infinity, while for a system type 0, it is a finite value. Okay, so type has effect when omega goes to 0, while order has effect when omega goes to infinity. So hopefully I could clarify. They affect the two endpoints of the graph. Now that we have seen the Nyquist plot, let's look at one last plot that is common in frequency domain analysis, and that is called like magnitude versus phase, or sometimes called Nichols plot. So Nichols plot is very similar to a Bode plot, but here, as you can see, these three graphs against each other. In Bode plot, we plot the magnitude and the phase, each one separately against omega. In Nyquist, we did the polar plot. Now in Nichols plot, we do something very similar to Bodhi, but we collapse the two graphs into one and get rid of omega. So the y-axis is magnitude and the x-axis is phase, and omega is implicit. Again, like the Nyquist plot, omega is implicit. So at any point here, I have some omega, but I don't know it. In MATLAB, you can click on it and you can see it, but at any point when I have some omega, then it gives me a magnitude and a phase, and then I plot magnitude versus phase. So this is like a brief version of Bodhi plot, okay? And this has its own advantages, and the command Nichols, as I said in MATLAB, can give you this curve, and I'm going to show you that before we finish this lecture. So here, if I define the system again to be the first order system, now I can say what is the Nichols of the system. And there we go. That is the Nichols plot for a first order system. You clearly see the x-axis are angle and the y-axis are decibel. And if you want to know the frequency at any point, you click on data tips and you click at any point. It will give you magnitude, phase, and the frequency. Okay, so it's implicit, it's hidden in it, but you can see it here. So when I go to this side, omega goes to infinity, while I go to the other side toward origin, omega goes to 0. Okay, so hopefully you have learned the three different types of plot, Bodhi, Nyquist, and Nichols, and we're going to use them extensively in this chapter. So I'll see you in the next lecture. Thank you so much.